Okay, wonderful. So I guess I should go ahead and share the slides here. So let's see. Doing. Okay, great. So thank you, Yi, for the introduction. And welcome everyone. I apologize for not being able to be there in person, but it's wonderful to join virtually. So as you mentioned, this first day of the workshop is more or less going to serve as a kind of educational tutorial. So we have a slate of 7 talks lined up here. The speakers are on the slide. Great bunch of folks. Unfortunately, it's a little bit late here, so I don't know if I'm going to be able to stay awake for all of the talks, but it's really a nice schedule. So what we're going to do in this first session of the tutorial is to basically outline at a high level some of the fundamental models and theoretical results around sparsity and low dimensionality. So I'm going to try to motivate a lot of what you'll see later throughout the day, while also kind of putting it in historical context and talking a little bit about what are some of the basic sparse and low dimensional models, where do these arise historically? What do we know about them? And then as we move forward through the day, we'll see what are some of the practical, efficient, scalable computational tools for interacting with these models. How do they shed light on phenomena in deep learning, both in understanding how neural networks train and in understanding how to design neural networks? And then finally, how do you specialize or customize them both to building very efficient neural networks and to building task-driven networks for problems in imaging. So the kind of broad arc here is going from fundamental, but kind of a little bit idealized, to very practical and applicable. And so this is the first lecture. We're going to talk a little bit at a high level about low-dimensional models, right? This is a conference and a tutorial on low-dimensional models and deep learning, right? Sparse and low-rank modeling. And so, when I think about models and data models, I sort of think about these as touching every part of our data or signal processing pipeline, right? As we go all the way from sensing and signal acquisition, how do we get the continuous world into the computer, to how do we pre-process, improve, beautify the signal, all the way up to how we make inferences and make predictions. All along this processing chain, we're leveraging different structure in the signals and in the sensing process. And so what we'll try to argue through this tutorial is that this pursuit of low dimensionality, of structure in signals, structure in data, structure in networks, is actually kind of a universal task in data processing, right? Anytime we're doing something statistically sensible in high dimensions, we're using some kind of low dimensional structure. And so a lot of our task here is going to be to make some of those models explicit, understand how we can derive and apply them correctly, and then understand how to compute efficiently with them at large scale. Okay, now this notion of looking for low dimensionality, of course, this is the 3rd iteration of the workshop. It's been running for a couple of years, thanks in large part to the amazing efforts of Ching and Yi and others. But of course, pursuing low dimensionality didn't start here, right? This is a very old activity that has roots in a number of different fields. Here in signal processing, whenever we think about historically about how to process signals, it's really about finding representations that best match and best reveal the structure in signals. So if we think about, in our signal processing course, a Fourier or a wavelet representation, right? This is good at representing smooth or piecewise smooth signals. And as we try to move forward to capture more and more structure of signals, to be more efficient and effective at compression, at denoising, et cetera, a lot of this has to do with deriving better models for the structure of the signals, both analytically and later on, as we'll see in the later part of the tutorial, by learning from large data sets. And as we'll see, there's a really kind of beautiful and fundamental connection between these learned low-dimensional models and what we do in deep learning. And this is kind of a bidirectional connection. If we have the right signal model, we can leverage it to derive and or train effective neural networks. And conversely, if we have an effective neural network, whoa, I can see that okay, we just took the limit as n goes to infinity. If we have an effective neural network, often there's some kind of a sparse model under it. Okay, so this isn't signal processing, but of course the notion of low dimensionality is not unique to signal processing. This is very fundamental in neuroscience, right? A lot of how we understand the early layers of the brain, say in the visual cortex, is in terms of sparsifying images, right? Looking for an efficient representation of the sensory input. And of course, sparsity and low dimensionality also play a very, very fundamental role, both in classical and modern statistics. We're going to talk a lot about sparse models in this tutorial and in this workshop. Sparsity in statistics corresponds to selecting a few relevant predictors, right? What are a few variables that describe what's going on in my observed data. Also, a close cousin of sparsity, low rank or low dimensionality, plays a fundamental role in selecting directions of large variance in data sets, right? PCA is basically fitting a low rank model to data. Okay, so historically, a lot of statistics has really been about capturing sparse and low dimensional structure in data. Now, in both classical and modern statistics, we often have to do this in somewhat unfavorable circumstances. Especially in modern applications, we often have lost control of the data collection process, right? We have a ton of data, but it may not be completely reliable. So we sort of have to work not only in the presence of noise, but also of errors, corruption, maybe missing or incomplete data. And this effort to try to be as robust as possible also has a very long and very rich history. We're going to talk about sparse regression, and some of the oldest works on sparse regression actually come from this literature on error correction, going back at least to the 1700s. And so, we're going to talk about some of the new stuff, but it's worth noting that this broad goal of modeling structure in data, of finding structure in data, is one that people have been after for centuries. And so I think what's really new and exciting here is, not just that we're after the right representations for data, that we're finding structure in data, but the tools that we have available to do it, right? The reason that we have a workshop is because over the past, say, 30 years or so, we've had really incredible advances in computing, incredible advances in our data collection capacity, right? So we're able to process very large data sets. We're able to compute with very large data sets, right? This is, making neural network, especially deep neural network training, effective and sort of practicable at scale. And as we'll see, at the same time, some of the fundamental computational methods and theoretical tools have really matured. So, not only are we able to compute dramatically more interesting things at dramatically more interesting scales, but increasingly we have available to us tools for understanding when and why that will succeed. And the the quest to sort of understand how these tools can guide the design of deep networks, how they can sort of help us to choose the right network components, the right training algorithms, and how we can use them to understand not only how to train large networks on huge data, but how to maybe minimize the size of the network, minimize the data cost, the computational cost, the energy cost, is going to be a theme for this tutorial and for this workshop. Okay, so, again, quest for low dimensionality in signals has very old roots: statistics, neuroscience, signal processing. What's sort of new and exciting here is our ability to do this with very large, potentially nonlinear models at very large scales. And so this new context of really big data and really potentially complex models raises some questions. And so these are kind of motivating questions for this sequence of tutorials and for the workshop. One very basic one is, how do we know we're computing the right thing, right? So when we talk about computing with various types of low dimensional structure, we want to find a sparse vector. We want to fit a subspace to data. How do we know we've got the right vector? How do we know we've got the right subspace? So how do we know we compute the right thing? Okay, so that's a kind of basic issue. At least as important, if we're talking about large data, is how we make sure that we compute that correct thing efficiently. And for us, this is going to be largely about understanding the structure and solution of optimization problems, right? We're very familiar, if we're working, either in classical signal processing or in deep learning, with the notion of fitting models to data, right? Almost everything we do boils down to optimization. Also, as we go through the tutorials, we'll see that in some situations, we can actually interpret our data processing strategies as solving optimization problems. So in my deep network, my sequence of layers actually corresponds in some sense to iterations of an optimization method. And so this really puts a premium on understanding the structure of optimization problems that we can solve, right? Because we know that optimization in general is impossible, especially in the context of fitting deep networks and learning models from data. Usually the optimization problems we encounter are non-convex. And so understanding what are non-convex structures that we can work with, when can we efficiently fit these nonlinear kind of compound hierarchical models, is going to be a theme. And this is going to be a major theme for the second lecture. So the second lecture is going to be all about both structurally and computationally, what are non-convex optimization problems that we can solve efficiently in a strong sense. Okay, so motivation 1 is correctness. Motivation 2 is efficiency. Then, in addition to computational efficiency, if we're talking about large, flexible models, we have to think a lot about resource efficiency, right? A lot of the value of low-dimensional structure in problems and data sets and in models is that it allows us both to quantify what is the minimum for my problem, right? How much network do I need? How much data do I need? How much compute do I need? And can I guarantee that I'm hitting that minimum? And I think, as folks will argue across the tutorial and across the workshop, this is becoming an increasingly important direction, right? Our practice of deep learning over the past, say, 10 or so years has been largely driven by scale, right? More data, more compute, more model. But as we start to run into barriers associated with that scaling, it's becoming increasingly important that we figure out what is the minimum. What's the minimum network? What's the minimum data? What's the minimum compute? And so understanding how architectures interact with problem and data structure is going to be a theme. In particular, this is really going to be the motivation for lectures 3 and 4 of this tutorial, where we sort of try to look both in a kind of input-output perspective, and then look at the features in a deep network that are learned and see how those adapt to structure and data. Then in lecture 5, we're going to see how we can leverage that to design deep networks that are effective for particular data structures. Okay, so our third motivation is efficiency. Then a fourth motivation, which we'll see a lot of in this talk, and then in a few of the future lectures, is robustness, right? As we mentioned earlier, increasingly our data are not curated for a particular task. Rather, they're kind of uncontrolled. And so we need some way of coping with errors, with outliers, with missing data. And here, again, what we'd like to argue across the sequence of tutorials is that low-dimensional structure plays a critical dual role in robustness. If I talk about correcting for a certain type of error, say in the image at the top of the slide, I have an occlusion. Well, if I want to compensate for that error, if I want to perform recognition despite occlusion, if I want to cope with noise, with missingness, I need to leverage two types of structure. One is the structure of the clean signals, right? If the clean signals are not structured, then there's no way that I can distinguish an error from a legitimate signal. The other type of structure is the structure of the errors themselves. As we'll see, missingness, occlusion, corruption actually do have specific low-dimensional structure associated with them. And it's really by leveraging these two complementary forms of structure that we can have robustness in a strong sense. Okay, so our fourth motivator here is robustness. And maybe the fifth, which is a little bit specific to computer vision applications, but shows up in other guises, for example, in applications with physical data, audio, et cetera, is invariance, right? How do I make sure that my network architectures are invariant to the things that they should be invariant to? Here, looking at the particular example of invariance to visual transformations, say to image rotation and scale. And this is one of those kind of recurring issues where, when we design or learn deep networks, there's always going to be some component of this process that is data-driven, right? I need data to tell me what that set of clean signals or untransformed signals looks like. At the same time, there are certain nuisances that we know ahead of time will be present. And so how do we make sure that we are handling those in a principled fashion? How do we make sure that we have uniform performance across all legal perturbations of my input? Okay, and so again, this boils down to leveraging two complementary types of structure. One is structure in the clean signals. The other is structure in the allowable transformations. And here, this structure is going to be a particular type of nonlinear structure, right? If I think about transforming an object in an image, in the image space, this actually ends up cutting out a low-dimensional manifold. And so in this particular setting of invariance, we're sort of asking, how do we compute correctly with data with manifold structure? Okay, so that's kind of a mouthful, right? We have at least 5, what I would argue, pretty important motivations for looking at low-dimensional models and their interactions with deep networks. We're going to kind of walk through this at a somewhat leisurely pace across the 7 tutorial lectures. Again, the goal of this lecture is just to introduce a few of the basic models. We'll talk a little bit about sparse and low-rank models and how they can be combined in interesting ways. Then in the next lecture, we'll talk about computation, in particular, non-convex optimization for low-dimensional models. Then lectures 3 through 5 will look at interactions between deep learning and low-dimensional structure. Again, how we can use low dimensionality to understand how generic deep networks train, and how we can use it to design effective networks for tasks. And then lectures 6 and 7, you can kind of see as a deep dive both into how we design efficient networks and how we leverage connections between deep networks and inverse problems to build highly effective networks for tasks and imaging. So this is kind of the plan for the tutorial. For the first few lectures, one resource that's available is this book, which is joint with E, who introduced the talk. This is high dimensional data analysis with low dimensional models. If you'd like to learn more about some of the things that you're seeing across the tutorial, you can feel free to take a look at the book. And if you manage to grab a copy of the slides or just throw this into Google, there's a pre-production copy that you can take a look at that has all of the models that we'll talk about today. So this you can almost see as a kind of text for the tutorial and then some. Okay, so we have about 30 minutes remaining in this first lecture. And so, what we've done up to this point is more or less to set the stage. We've talked about some ways in which we would like to leverage structure in data sets and ways in which that might interact with deep learning. We've also talked a little bit about history of low dimensional models, just the fact that this notion of low dimensionality shows up in many different fields and has a very rich history associated with it. What I'd like to do next is dive into just a couple of fundamental low dimensional models. These are probably familiar to a lot of you in the audience. But if not, we'll try to just give a high-level introduction to a few models that we'll see throughout the day and throughout the workshop. Probably the most basic and most fundamental low-dimensional model is what we would call a sparse model. The notion of sparsity is just to say that a signal of interest has only a few important components. Formally, we'll say that a signal X, here we're visualizing it as a vector, is sparse if it has only a few non-zero entries. And of course, then a very important question is, what do you mean by a few, right? So we'll quantify that as we go, right? In general, we would like to be able to cope with vectors that are as complex as possible. But when we have some notion of sparsity in the problem, that's when we can really get away with estimation with limited statistical resources, limited computational resources. So sparsity, as we'll see, is going to be a structure that we're able to leverage again and again to do things that would not be possible with generic signals. Okay, so basic definition, vector is sparse if it has only a few non-zero entries. And probably the most fundamental problem associated with sparse vectors is this problem of recovering a sparse vector, here we're calling it X, from a few linear measurements, right? So here, written as a matrix equation, y equals ax. Now, of course, at least on the surface, this looks very simple compared to what we do these days in deep learning, right? This is in some sense, a shallow model, right? We just have a linear system of equations. And what we would like to do in this linear system of equations is go from y to x using the structure of x. The thing that makes this a little bit challenging and actually quite beautiful and interesting is that in most modern applications, the systems of equations that we encounter are actually underdetermined. We typically have fewer observations than we have unknowns in X. And so, as we'll see, it's going to be really critical that we leverage low-dimensional structure in X. If we know that X is sparse, then we'll actually be able to make some progress. Whereas for generic vector, we simply don't have enough information. Okay, so where does this sparse recovery problem show up? well, we mentioned that one historical source of sparse models is neuroscience. Here, this is a kind of cartoon neuroscience problem, a sparse deconvolution problem. So I have an observation which consists of spiking patterns that are the result of multiple neurons firing. So every time a neuron fires, I have some characteristic pattern. What I see is a superposition of those patterns stamped down every time I have a firing event, plus noise. And so here, the sparsity in this model is a sparsity of the firing events, that it's only at particular times that I have a neuron that spikes. So here, my X, my sparse vector that I would like to recover, is this spike train that tells me when the neuron is firing. My Y, the observation, is the convolution of that thing with the firing pattern. I want to go from Y to X. And so this is just one example of how these kind of low-dimensional models, sparse models, show up very naturally from the physical structure of data. And one nice thing about this area is that once you sort of understand those basic tools, you start to see the same models showing up in a lot of different places. So at top, we have this sparse model for neural spikes. In the middle, we have a sparse model for microscopy data. And here, this is coming from a completely different application in material science, where folks are trying to understand high temperature superconductivity. And for our purposes, the thing to notice here is that actually this microscopy data follows exactly the same sparse model, but now in 2 dimensions. For neural spikes, my sparse model was I have my spike pattern stamped down every time I have a spiking event. For microscopy, my sparse model is that I have these kind of characteristic motifs in my data set, here corresponding to this kind of 8-looking pattern that you see in the middle of the slide. And my observation is a superposition of those things stamped down at different locations. My data analysis task is to find potentially the locations and maybe also that pattern. So anytime we're finding motifs in data, we're kind of looking at some kind of a sparse model. Okay, so this is one source of sparsity. I can get sparsity from the physical structure of data sets, especially data sets that consist of multiple motifs. Another really natural source of sparsity that we kind of alluded to earlier shows up in error correction. So here, this is a kind of cartoon example from some older work on face recognition, right? Not state of the art right now, but kind of cleanly illustrates a few concepts. So here, this is setting up an image recognition problem as a kind of regression problem, where what I'm trying to do is to take my given observation, here that's this corrupted image at left, and express it as a superposition of some things that I've seen before, this sort of training data set in the middle, plus an error, which here is capturing occlusion at top and corruption at bottom. And I like this example because it kind of illustrates how sparse structure actually can show up in 2 different places when we go to compute with unreliable data. We have a form of sparsity in recognition here, just in the sense that we're trying to pick out one or a few pictures from a big data set that can explain this observation. For those of you who like to play with classification in deep networks, you'll notice this same kind of sparsity in a one-hot class encoding, right? There's a kind of sparsity from the fact that only one class is relevant to this image. And there's a form of sparsity that shows up in both occlusion and corruption. Occlusion, for example, can be very large in magnitude, right? If I cover this part of my face, those pixels are completely changed. On the other hand, only a few of the pixels are affected, right? There are some fraction of the pixels that remain clean. So we do well in this situation to model this error as large but sparse, right? We can't trust some of our observations, but it's only a fraction of them that are wrong. So this is an example of sparsity both in the signal and in the error. Okay, and this is just some examples of recognition by solving regression problems. I see there was a chat and then it disappeared. Okay. Oh. Okay. So this is just some kind of toy example of that, basically showing that if we have the right model and the right computation, then we can do quite good error correction by leveraging structure of the error. Okay, so we've seen a couple of forms of sparsity. We saw sparsity from motifs in physical data. We saw sparsity in recognition problems, right, through the class encoding. We saw sparsity of errors, right, occlusion and corruption. Sometimes we can find sparsity not in the original signal domain, but if we go looking for it in an appropriate transform domain. So this is a kind of canonical and very important application of sort of classical sparse approximation and compressed sensing tools. This is in magnetic resonance imaging. So, here the imaging modality, the physical imaging modality is kind of complex, right? It involves putting you in this machine, subjecting you to a space and time varying magnetic field. This, sort of creates an RF signal, which we can measure. And it turns out that that signal actually corresponds to coefficients of a Fourier transform of what is essentially the density of protons inside the subject. So, here, if we're trying to image inside this person's head, what we're getting is basically some entries of the two-dimensional Fourier transform of this picture of what's inside the brain. And so the inverse problem task here, which we'll see a lot in lecture 7 of the tutorial, is to go from those few Fourier coefficients, here few because you can't sit inside this machine for very long, to an accurate and high resolution image of what's inside the body, right? So it's basically like we want to hallucinate the entire picture from just a few coefficients of its Fourier transform. So this is a great example of how physical measurement constraints give us underdetermined problems. This is underdetermined as a system of equations because, again, I have just a few measurements and I have a very large number of unknowns. I have as many unknowns as I have image pixels. So to do anything here, we're really going to need to leverage structure of that image. Okay, and it turns out if you dig into the structure of these images, because they tend to be relatively smooth with a few sharp edges, these tend to be fairly compressible in a wavelet basis. So this is an example of even if I don't see sparsity on the surface in my problem, if I can represent my data in a compact way, if I can find an appropriate transformation of the data, I may find some sparse model under the surface. So here, the sparse model is sparsity in a wavelet domain. And that's something that I can leverage to reconstruct the picture from far fewer measurements, right? The way we would do it is by casting the sparse recovery problem as one of recovering those few important wavelet coefficients from these relatively few Fourier coefficients. So that becomes a linear system of equations. That's our underdetermined linear system. And what we're trying to do is to solve for those wavelet coefficients, that's our x, so that we can reconstruct the picture. Okay, so this is actually a very important and very practical kind of classical example of these tools. It also illustrates some of the challenge here, right? Because the structure of signals doesn't always present itself right at the surface for us to see, right? We may have to dig for the right representation. And so one very tempting idea is to actually let the data kind of speak for itself. So instead of needing to analytically define a good representation, maybe I can simply learn a concise model from data. So this is an example from image denoising. So here the data are patches of a noisy image. And what's being learned here is actually a kind of transformation, or more precisely, a dictionary, which can concisely represent those image patches. So what you see right here are actually the patches of the dictionary. Basically, the way that that's found is by saying, find me an A such that this collection of patches, yi, can simultaneously be sparsely represented as superpositions of those basic atoms in A. So basically, look for a concise representation. And if we've done a good job of it, that representation should capture the actual structure of the signal. And in this example, what you see in the middle is actually a denoised image. So this is the result of just keeping the sparse representation in that learned dictionary. And so what you can see is that actually, yes, the random noise in the original picture is mostly incoherent with the structure. And so because of that, when we go to learn a concise model, we keep the structure and not the noise. So it illustrates some of the utility of low-dimensional models. And it also says that if we have enough data, we can kind of let the data tell us how to find the right model, right? There are a lot of things that we may not need to model analytically. Of course, then that presents us with sort of new computational and statistical problems, because then a question is, how do we know that we've learned the right model, right? Yes, we can take our method and throw it at data, but how do we know that what we get is the right thing? How do we know that the computation is reliable? How do we make it efficient? So this is going to be largely the topic of the second lecture in this tutorial. We'll see a lot about dictionary learning, low-rank modeling, and then some generalizations of them. And we'll see actually how we can get a handle on the structure of these problems, leverage it to understand what we're computing, and leverage it to compute efficiently. Okay, so this is sort of a third guise of sparsity, right? Sparsity shows up in transform domains, and we can, in essence, learn to make those transformations. We can learn good representations for signals. Okay, now, how do we actually leverage sparsity computationally? Well, to do that, we need to be a little bit more formal, right? We've been kind of cartoony so far. We need a formal notion of a formal measure of sparsity. And probably the most natural one is the number of non-zero entries. We say that a vector is sparse if it has only a few non-zero entries. We formalize this through the so-called L0 norm, which here is just the number of non-zero entries in the vector x. So we denote this norm of x0. And as an exercise, you can convince yourself that that L0 norm is actually mathematically not a norm, but it has some of the same properties. One way to understand the connection of sort of L0 norm and more familiar norms like the L2 norm or the L1 norm is through the unit ball associated with the norm. In particular, at the bottom of the slide, we can see the unit ball of the L infinity norm, that's a cube, the L2 norm, that's a sphere, the L1 norm, that's a kind of octahedron, that's an important one. And if we take an LP norm, that's the pth root of the sum of the pth powers, and we send p down from infinity to 1 and then beyond, this norm ball sort of shrinks in and becomes more and more tightly aligned with the coordinate axes. And if you think about sparsity, sparsity says that my vector x uses only a few of the coordinate axes, right? Because only a few of the coefficients are non-zero. So you can think about LP for small p as being kind of close to those coordinate axes and hence doing a good job of capturing sparsity. Of course, as we'll see, when p is less than 1, our so-called LP norm is actually not mathematically a norm. It's no longer a convex function. And so that poses some challenges for computation. So often we'll kind of be looking for a sweet spot where we have something that is good at picking out structure, but is also well suited to computation. In particular, often for practical computation, we like the L1 norm as a convex surrogate. Okay, but in any case, L0 norm is our way of measuring sparsity. And associated with it, we can define a computational principle where we say, okay, if I want a sparse representation, right, I have some data, I'm trying to represent it efficiently, or I have a few measurements, I'm trying to find a sparse thing that agrees with them, as in the MRI example. Well, one very sensible thing that we could try to do is to look out of all signals that agree with our observations, look for the sparsest one. Find the one that minimizes the number of non-zero entries. Okay, and it turns out that often that's a sensible thing to do. So we won't go into too much detail on the actual mathematical statements, but in essence, if our measurements are generic enough, then if we look for the sparsest thing that's consistent with the measurements, that actually will be the correct solution. And generically, the number of measurements that we need is just a little bit more than twice the number of non-zero entries in the vector that we're trying to reconstruct. So what this tells us at a high level is that actually sparsity is a pretty powerful property for regularizing ill-posed problems, right? If I think about it, if I think, for example, about this magnetic resonance reconstruction example, and I ask, what dictates the number of measurements that I need to take? Is it the number of pixels in the image that I'm trying to reconstruct? That would be the case if I didn't use structure. Or is it the number of important non-zero coefficients? Is it the number of large entries in this signal's representation? What these theoretical results tell us is that it's the latter, right? What dictates the number of measurements that I need to take, the amount of data that I need to see, is not the extrinsic dimension of that signal, but actually the intrinsic dimension, the number of non-zero entries. Okay, and so that says that actually sparsity is very valuable as a regularizer. That's why, as we saw in the examples, we work so hard to find it in naturally occurring problems. On the other hand, this search for the sparsest solution kind of runs us up against some computational challenges. In particular, in general, finding the sparsest solution efficiently is impossible, right? When I think about that sparse approximation problem, right, this says out of all signals that are consistent with my observations, find me the one with the fewest number of non-zero entries. Well, this is really asking me to sort of select a few things out of many. So if you imagine intuitively how you try to do that, if we didn't know anything about the area, we would just sort of say, okay, try all collections of 1 entry, 2 entries, 3 entries, right? There's kind of a combinatorial nature to this search. And unfortunately, or maybe fortunately, this notion of sparsity is so powerful that there are a number of combinatorial problems that are believed to be intractable, which can be reduced to it. So this is just showing a kind of theoretical computer science flavor example of this, which sort of shows the computational hardness of L0 minimization by reducing from a combinatorial problem that's some kind of a set cover problem. Okay, and so this, here for our purposes, we're not so focused on the details of this, but just to say that it's not enough for us to have an effective regularizer, an effective low-dimensional model. We also need to be able to compute with it. And what this says is that we can't directly compute with the L0 norm, right? We need some kind of a tractable surrogate. And so, classically, one effective way to do this is basically to look at the class of functions that I believe that I can optimize, which is often taken to be the convex functions, and then look for one that's a good approximation to the number of non-zero entries. And so the number of non-zero entries, here this is plotted in red as a function of a scalar. So along the x-axis you have t, and then the red thing is the number of non-zero entries in t. And if I imagine that t is bounded between -1 and 1, and I ask, okay, find me the tightest convex lower bound for that number of non-zero entries, it turns out that that tightest convex lower bound is actually the L1 norm, the sum of the magnitudes of the entries. We can also sort of see this in terms of this figure at Wright with the norm balls, where we said that as p goes from infinity down towards 0, we get a sequence of geometric objects which get closer and closer to the coordinate axes. And p equals 1 is this kind of nice sweet spot where I have a convex body. I have kind of an octahedron, or, here in 2 dimensions, a diamond shape. So we're convex. That's good for computation. On the other hand, we're as close as possible to those coordinate axes. So maybe we're good for finding the sparse things. And one of the big surprises in this area is that although we can't recover all of the sparse things, right? We argued a few slides ago that that problem is hard in general. Actually, there is a fairly well-structured subset of them that we can find. And it turns out that often they're the ones that we're looking for. And basically, the intuition is that for solving systems of equations y equals ax, if A is nice, generic in some sense, then this L1 minimization, the thing that I actually can compute with, is capable of finding sparse solutions to this system as long as my number of observations in y is a little bit bigger than the number of non-zero entries in x. Here, not as small as twice as large, we have to pay a little bit more, but, say the number of non-zero entries times the logarithm of the length of the vector. So this plot here is just sort of showing this. Here we're varying the complexity of the signal that we're trying to recover. And what we can see is that actually there's this sharp transition between always succeed. We always succeed when the target is structured. we always fail when it's unstructured. And so in some sense, this is good news, maybe even better than we could hope for, that although the worst case is hard, if our model is well motivated, if the target signal is structured, then we can get at it with tractable methods. And, this is, again, very classical and pertaining to a relatively simple data model, right? Linear system of equations. But this is a theme that we're going to see again and again throughout the lecture, or throughout the tutorials, that structure makes computation possible and efficient. So structure is good for us statistically, and it's good for us computationally. Okay, and so there's a sort of beautiful geometry associated with this that basically explains why this is working. I won't go into it in too much detail, just to say that the fact that the L1 ball is pointy makes the L1 norm good at picking out sparse things, right? And it actually is what makes L1 well motivated in this setting compared to something like L2. Okay, and as we go to quantify this, then a little bit heavier theoretical machinery is required. In particular, the notion that we should have in mind is kind of a notion of isometry. What that means is that our measurements are preserving the structure. So here we have the sparse things. Those are the structured vectors that we would like to recover. And what we need to be able to efficiently recover them is that our measurements actually preserve their geometry in a particular sense. And this, again, is a theme that we'll see throughout the sequence of tutorials. In fact, when we get to deep networks, we'll see that a lot of what makes deep learning sort of work at the optimization level and what we can try to design for at the sort of individual component level is really preserving the structure of signals, right? We want to sort of make sure that things stably propagate up and down our network. So, here in this simpler setting of sparse approximation, we're really trying to preserve the structure of the sparse signals. When our measurements do that, then we can do a good job of going from the measurements back to that structured signal. Okay, so we won't talk much about the theory here, but just to say that all of this can be quantified, and the mathematics associated with it is actually really beautiful. I personally learned a lot by learning this area, so it's a lot of fun. But I think what I'd like to do with the remaining maybe 3 minutes of this introductory talk is just sketch one generalization from sparse to low rank. So we talked a lot about sparse models. We saw that these show up in a lot of different physical scenarios. But sometimes we need other things. And so what I'd like to show in the next few slides is how this notion of sparsity generalizes very naturally from a single signal, that's the single vector X or a single image, to a batch of signals. And that batch of signals we're going to kind of represent as a matrix. Okay, and so for low-rank modeling, there are really nice motivations in imaging, in collaborative filtering, recommender systems, so on and so forth. I don't have time to sketch them in too much detail, but hopefully the slides will be available, and you're also welcome to check out the book. But the point is that this is a very fundamental class of low-dimensional models, right? Modeling a collection of images, a collection of user preferences as lying on a low-dimensional subspace. And it turns out that this is actually a kind of sparse model as well. So when we talk about low-rank models are sparse, not in the in terms of the entries of the matrix, but rather in terms of its singular values. So if I think about a matrix X and I think about its singular value decomposition, the rank is the number of non-zero singular values. And so my matrix X is low rank if and only if its singular values are sparse. And so that means that all of the same intuitions and even computational tools that we've alluded to over the past few slides can also be deployed in this setting. We can talk about recovering low-rank matrices from a few observations. We can develop good computational approaches. Again, understanding when our observations interact nicely with that low-rank structure is important theoretically. And this actually leads to very practical and sort of scalable and statistically principled approaches to a lot of different applied problems. Okay, so there's a kind of high-level message here, which is a parallelism between rank and sparsity, right? This the workshop title is sparse and, I guess, sparse and low-dimensional deep neural networks. And so what this slide is kind of arguing is that actually sparse and low rank or low dimensional are sort of two instances of the same thing. They're both a form of sparsity. And it turns out that there are a number of very powerful generalizations of this. If we have sparse and low rank, we can look at things that are both sparse and low rank, have superpositions of this. We can model structured batches of signals and errors. This is especially applicable in video analysis, community detection, so on and so forth. We can talk about structured forms of sparsity, incorporating more and more signal structure. This is especially important in imaging, where there's structure on those wavelet coefficients, there's structure on the occlusion. This can be modeled in a kind of sparse model. As we talked about earlier, we can learn models from data. And finally, as we move forward through the lectures, we'll talk more and more about deep models for nonlinear low-dimensional structure. We'll see that some of the same themes, modeling structure, isometry, understanding propagation of information, understanding how many measurements we need, come back again and again as we try to do this. Okay, so with that, thank you very much for your patience with the remote talk and also your attention and attendance. I'm going to stop here. This is actually something like a 500-page story. So if you want the full version, you can feel free to check out the high dimensional data analysis book that was alluded to earlier. Our next lecture is going to go into computation and modeling with non-convexity. So, moving in the direction of non-convex and eventually deep. And so with that said, thank you very much. If time permits, I'm happy to take any questions if folks have questions. And yeah, thank you.